Hello and welcome back. And today, as always, we have an awesome guest. So please, introduce yourself.
Hello.
Sorry about that. That always happens. I'm here to talk about statistics. I'm an expert.
I don't know about you, but I'm excited to start talking about stats, huh?
But like, statistics is the best. There's nothing boring about it. You can learn. You can even know what things weigh. It's amazing!
Generalized linear models. And here are our objectives. Understand the difference between random, link, and systematic components of a model. Understand the difference between transforming y and the expectation of y. Understanding under what conditions you'd use a poisson, negative binomial, etc. Understand how to choose between different families of distributions. So those are our learning objectives.
Those are fantastic learning objectives.
Right you are, good sir. So what the blimp is a GLM anyway? Well, GLMs, or generalized linear models, in standard linear models, or general linear models, not generalized, but general linear models, we assume the data are normally distributed. If data are normally distributed, we know how likely it is to have, for example, a standard deviation of, say, 1.96, or the probability of having a 1.96 or higher being equal to an alpha level of 0.05. So all statistical conclusions are based on how frequently scores of a particular z fall. Makes sense? But what if the standard normal distribution doesn't fit? Then the alpha level will not be 5% anymore. Y'all want to see a picture? I know I do. Look at that, people. So the red is a normal distribution, and the black is a beta distribution under some sort of parameters. And the blue line is the critical z of a normal distribution. Now notice that the area under the curve for the normal distribution, the red, is probably not going to be the same as the area under the curve for the black. So if that is 5% under the normal, it's probably not going to be 5% under the beta. So type 1 error probabilities are probably going to be messed up. But you know what? Confidence intervals are going to be messed up too, because the t distribution, the z distribution, or whatever plays into the confidence interval. But even then, your estimates are going to be off. Everything's going to be off. So if you're in a situation like this where the residuals are not normally distributed, well, you best be using something else, my friends. So take-home message, the probability associated with extreme scores on a normal will probably not be the same as extreme scores on a beta distribution, or a poisson, or a gamma, or a zero-inflated, etc., etc., etc. So when you use GLMs, we use them if the residuals are not normally distributed. Instead, we want to use GLMs, or generalized linear models. So some examples here. Let's say we're predicting death from heart surgery is a binary variable expected to be normally distributed. I don't think so! What about predicting sexual assault? Do we expect assault to be normally distributed? Boy, I hope not! Because most people will probably not do anything close to sexual assault, and then less and less people will do extreme instances of sexual assault, as you see on the graph on the left there. Or another example might be predicting the number of times someone seeks therapy. Most people don't seek therapy, and the probability shrinks as the number of times increases. So these are situations where we would use GLMs. So how do you model that?
There are 3 components to a generalized linear model. The first is the link function. The second is the whatever that was. The distribution of the residuals. Third is the part you are all familiar with.
So right you are! So there is the systematic component, which is the part that we are all familiar with. This is the part of the model where the prediction equation goes. So in the past, we've seen equations like B0 plus B1 times depression plus B2 times anxiety. Well, guess what, folks? When you're using a GLM, it's exactly the same. Woohoo! So it's going to be a B0 plus your slopes times your variables. Same. Nothing complicated there. That's awesome. What is different, however, is the link function. So the link function is some fancy mathematics that bends the line. So on the right there, you see several examples of ways that you can bend the line. So the top left is y is equal to x squared. Top right is the square root of x plus 10. And I did x plus 10 just because you can't take the square root of a negative number. And otherwise, the mathematics cries and stuff. And then we have the exponent, and then the inverse function, and then the logistic or the logit function at the bottom left, and then the log function at the right. So often we use link functions to maintain the proper interval. So for example, the logistic, it should not go higher than 1 or lower than 0 because your probability can't exceed 1 and it can't get below 0. And so we use the function e to the b0 plus b1 times x divided by 1 plus e to the b0 plus b1 times x, etc. So that's the link function. And then third, what was it again?
The distribution of the residuals.
So how are the residuals distributed? Are the residuals distributed as a normal? Are they distributed as a beta, as a gamma, as a binomial? I know. This is all like scary terms and stuff.
Don't be overwhelmed, folks. It's okay. It's just a poisson, or a gamma, or a negative binomial, or a beta even.
Exactly, like my buddy here just said, no need to be scared, folks. So in ordinary regression, we've actually been using GLMs all along, generalized linear models, because general linear models are a special case of generalized linear models. So our systematic component in the past has been, for example, B0 plus B1 times depression plus B2 times anxiety. And our link function was the identity function, which just means you multiply everything by 1. If you multiply everything by 1, it just stays the same. And the random component was the normal distribution. So that's all there is to generalized linear models. And so here are some examples of different distributions. And by the way, one thing to be clear here is you don't like look at the distribution and say, oh yes, that must be a Poisson distribution or that must be a gamma distribution. I'm not expecting you guys to do that. Because here's another thing, is you can make just about any distribution look like a normal distribution with the right parameters. You can make a Poisson distribution look normal. You can make a binomial look normal. And so you're not supposed to, I'm not asking you to look at a distribution and say, oh yes, I intuit the shape of the distribution or the family of the distribution or whatever. You don't have to do that. These are just kind of examples of how they might look. For example, the bottom right, a beta. That is a beta distribution under certain really weird parameters. But it's going to change shape if you change the parameters. Just like with the normal, you can change the parameters. You can change the mean and the variance to give it a different location or a different spread. One thing about the normal is it is always symmetric, whereas the other ones may or may not be symmetric depending on what the parameters are. So, what is the difference between a link and a transformation? I know you're asking, folks. So, a link function is different than a transformation. So remember, we used to transform the dependent variable if it wasn't normal, like we used a Box-Cox transformation or something like that. Now, a log transformation is not the same as a log link. What is the difference? Well, if you do a log transformation, you are transforming y itself. So, for example, you might say the log of y, which is equivalent to saying the log of b0 plus b1 times x plus e. Because remember, that is our prediction equation, and we add e in there just to represent the fact that that's what y is equal to. So that's what a transformation looks like. Whereas a log link, you don't transform the e. You say log of b0 plus b1 times x, or a different way to put it is you transform the expected value. An expected value is another fancy way of saying the mean. So you are transforming the link minus the systematic component, which is equal to the mean of y. So is e included? If so, it's a transformation. If not, it's a link. Make sense? More on link functions. So different distributions have different default link functions. So here on the right, these are R's default for different link distributions. So for a general linear model or a regression or ANOVA or a t-test or whatever, the link function is the identity function, which just results in b0 plus b1 times x, and the assumed distribution, the assumed distribution is the normal. With the logistic regression, the link function is called the logit. It's e to the blah divided by e to the blah. And that distribution is the binomial distribution. And then a poisson, the default link function is log, which means, well, I'm talking about the the natural exponent here, but anyway, it depends on whether you're talking about y or the expected value of y. Anyway, so e to the b0 plus b1 times x, that's the link function, and the distribution that we assume is the poisson. And then the gamma is, its default link function is the inverse, which is 1 divided by b0 plus b1 times x, and the distribution associated with a gamma is, not surprising, a gamma. And it's kind of odd that somehow culturally things worked out this way. We call logistic regression, which is named after the link function, the logit function, and yet we call poissons, gammas, betas, all that after the distribution, not the link function. Go figure. So how do I know if the link is a good one? Well, for now, just stick to the defaults. R chose those defaults because they're probably pretty good defaults. In general, the type of analysis dictates the family. So really, you don't have to generally choose what the link function is going to be. Instead, you choose the analysis and the family chooses the link for you. But also, I would look at the visuals. If the fit of the line doesn't pass through the center of the data, then maybe you should try experimenting with different link functions, or maybe even different families. So now, again, like I said, you don't have to worry about the link function. You don't have to worry about choosing the link function for the most part. Instead, you have to worry about choosing a family. So how do you choose a family? And by the way, when I say family, I'm talking about what distribution of the residuals. For some reason, statisticians call it the family. So how do you choose a family, or how do you choose a distribution for the residuals? Well, let's just go through these one by one. With the binomial distribution, we call this the logistic. It is great for binary outcomes. And the link here is the logit. And we are very familiar with this logistic regression because we covered it in detail last week, so I'm not going to go into much more detail on that. Deal? Now a Poisson distribution or a Poisson. I like saying Poisson. It just sounds cooler than Poisson. Sounds like I have some sort of a speech impediment if I say Poisson. The Poisson. The Poisson distribution is great for skewed, discrete distributions. And the default link is the log, and we typically use this when we have count data. For example, the number of times you visited the doctor in a year, the number of times you have been to Disneyland, the number of times you have attempted suicide, the number of times blah, 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 blah. And the Poisson distribution, we make a critical assumption. We assume that the mean of the distribution is equal to the variance of the distribution, which we'll talk in the next slide why that might not be, or why that's an important assumption and how we can generalize that. So on the right there is just a graphical depiction of the criminal data set that I simulated in R, and it shows a relationship between socioeconomic status and convictions, and that is modeled with Poisson regression. Now that brings us to the negative binomial. So the negative binomial, doesn't that just sound cool? Like negative binomial. You can impress your friends when you say, I ran a negative binomial distribution with a log link in a generalized linear model, and I found that that fit far better than a Poisson distribution when I used the AIC, BIC, and Bayes factor calculations doing my model comparisons. Wow, I just sounded smart. Okay, So negative binomial, it is also good for discrete distributions. And what I mean by discrete is you have count data, you have integers, you have 1s, 2s, 3s, 4s, that sort of thing. You don't have 1.2, 1.758432. If you have any sort of data like that, logistic and the negative binomial probably aren't going to work. So default length for the negative binomial is the log s, and it has two parameters. S is the number of successes, and P is the probability of success. I'm not going to go into details on what those, but basically as you change those two parameters, the distribution may look more and more normal, more and more skewed, depending on how those things are put into the equation. So it is often a good alternative to the poisson, because here's the important thing, is that a negative binomial does not assume that the mean equals the variance. So, wow, this is sounding like a whole lot of technical stuff right now, so let me just pause. Take a deep breath. We're good. So far we've talked about the poisson, negative binomial. If you have count data, or if you have discrete values, 1, 2, 3, 4, 5, I would probably model it both with a poisson and with a negative binomial, and then you can do a model comparison and see which model is better. A-okay, we're good. Don't need to worry about it. So now that brings us to a gamma distribution. Well, what happens if you have skewed non-discrete data, if you have skewed continuous data? What do you do then? Well, then you can do a gamma distribution. So gamma is great for skewed continuous distributions. The default length is 1 over x. At least it is in R and SPSS. I think it might be the log of x or something like that. Remember, so we are using a length function, or a length function that is an inverse. And so what happens is when you compute the coefficients, they will actually be reversed because it is inverted. So they might all come out negative, when in reality you have a positive relationship between the two. So for example, in the image on the right, we have a negative association between empathy and aggression. As people's empathy scores go up, their aggression goes down. But if you were to use a gamma distribution with an inverse link, then you would find that coefficient would actually be positive. So you have to reverse that in your mind. Also, by the way, the gamma distribution, by definition, is strictly positive. So gammas are always positive. So if you have an outcome variable that is negative, R will bark at you and it will refuse. It will like cross its arms and say, I ain't doing it. And so sometimes you have to, like let's say the minimum score is -10, you might have to add 10.5 or 11 or something like that to make them positive. That's just the nature of the gamma. Ordered logistic. So ordered logistic is a nice alternative to the gamma. It is, well-ish. The ordered logistic is great for discrete numerical outcomes, kind of like a poisson or a negative binomial. And higher values mean there is more of that income. So it's an ordinal. So you know, back in like intro stats, we talked about nominal, ordinal, interval, and ratio scales. Well, ordered logistic is for the second category. So if you have Likert scale data or something like that, or even most measures in psychology, they probably do well to be ordered by, or to be modeled by, an ordered logistic. If you suspect that the interval between time points is not equal, like the difference between 1 and 2 is probably not the same as between 2 and 3, ordered logistic is perfect for that. That's what it was designed for. So I often default to an ordered logistic if I have skewed data. Or another thing that happens is, technically when you're doing statistics, you should not have, when you're using general linear models, you should not have a minimum value and a maximum value. So theoretically, you could go any value to -infinity and any value to +infinity. But sometimes the scales that we use cut it off at, you know, if you've got a Likert scale from 0 to 10, you can't get lower than 0, you can't get higher than 10. Well, that actually can mess things up in general linear models. So ordered logistic would be great for a situation like that. So ordered logistic is an extremely flexible GLM. Doesn't really make any assumptions. And basically what it does is it is a logistic regression on steroids. So what it's doing in the background is it is fitting a bunch of logistic regressions for each level. So let's say you've got a Likert scale from 0 to 10. It's going to fit a logistic regression and say, is your score 0 or not? And then once it fits that logistic regression, it's going to say, all right, are you a 2 or not? Technically, I think it's a 2 or higher, or a 1 or higher. And then it says, are you a 2 or higher? Are you a 3 or higher? And then it just does that a bunch of times until it covers all its bases. So on the right here is an example of looking at the relationship between socioeconomic status and aggression for various levels of empathy and depression. And I'm just overlaying the predictions of the GLM. So GLM, in this case, it was a gamma. And I should probably change that in the Pfeiffer function to be a little more specific than just saying that it was a generalized linear model. Anyway, so the red is the gamma and the blue is the ordered logistic, and yeah. So oftentimes they will be similar, but like I said, the ordered logistic is more flexible. So what about multinomial logistic? Well, I don't have a plot of that on the right there. So that's why that guy is doing this. Anyway. Multinomial logistic, it is very similar to the ordinal logistic, or what did I call it? Ordered logistic, ordinal, ordered, whatever you want to call it. It is also used for discrete numeric outcomes, but the categories are not ordered. So with ordered logistic, you are on an ordinal scale. You know, there are innate quantity differences between the values of the scale. Whereas with the multinomial, it's not. So you might use multinomial to predict who's a Democrat, who's a Republican, who's a Libertarian, who's an independent, that sort of thing. So it is also a very flexible GLM, and like the ordered logistic, it too fits a bunch of logistic regressions at each level. Are you a 0 or not? Are you a 1 or not? Etc. And I'm going to talk about one more. And again, I don't have a graphic for this one either. This is a zero-inflated with zero-inflated models. ZF should be ZI. What am I doing? With ZF models, we assume two processes generated the data. One process that determines if the outcome actually occurred, and one that determines the degree to which it occurred. And I actually ran into this a year and a half ago. I had a student who was looking at non-suicidal self-injury, so people who hurt themselves, not with the intention of suicide, but just like cut themselves or whatever. And it seemed to me, I mean, this was a perfect situation for zero-inflated because there is a very big difference between those who engage in any NSSI and those who do not. But the student also wanted to predict the degree to which they did that. And I thought, you know, at the time, I didn't know about zero-inflated models. I was like, that'd be so cool if there was a model that could like do a logistic to figure out who does and who does not, and then fits like a gamma to figure out how much they do it. Well, it turns out that's exactly what a zero-inflated model is. So a zero-inflated model breaks it up into two components, those who do versus do not, and then it then tries to, of those who do, it tries to model how much they do. So the logistic predicts the presence, and then the other models, whether it be a gamma, a poisson, a negative binomial, whatever, predicts the degree. So in summary, these are our generalized linear models. If you got a binary outcome, for example, dead versus not dead, we're going to use a binomial family or a binomial, assume binomial residuals with a default link of logistic. If we've got a skewed continuous outcome variable, we're going to use a gamma with an inverse link. If we've got count data, for example, the number of incidences of rape, we're going to use a poisson with a log link. Or we might use a negative binomial when the mean is not equal to the variance. And like I said, you should probably fit both. And we use the default link of the log. And then we've got discrete outcomes. Discrete outcome variable with any shape of distribution, and the outcome is ordered. In that situation, we use an ordinal logistic or an ordered logistic with a binomial link. If we have discrete outcome variable with any shape of distribution and they are not ordered outcomes, then we can use the binomial family again with a multinomial logistic. And finally, if we want to predict the presence of something and the degree, and we suspect that those are two different processes, Then we're going to use a zero-inflated model. Default link. That's kind of a misnomer there, isn't it? Anyway, I guess the far right should say, what is the name of it? Anyway, my table's messed up. That's okay. So if we're predicting the presence and the degree, this zero-inflated model, we're going to use the logistic and one of the other ones. So just let's step back for a minute. I know it's overwhelming. GLMs can be overwhelming, but here's the thing. Okay, let me talk big picture for a minute. So 2 years ago-ish when I was designing this course, it's technically called multivariate statistics, and I had some moments of self-reflection. I said, all right, what do clinical psychologists, which are people that I'm teaching, what do they need to know the most? And then I said, okay, let me translate that. What are they going to be most likely to use? And I started thinking, all right, what do I see in the literature? Well, I see a whole lot of multiple regressions, so that's obviously got to go in there. I see a whole lot of mixed models. Those have got to go in there. I see a lot of situations where people should use robust stuff, so robustness should be in there somewhere. And honestly, I almost never see GLMs. If I see a GLM, it's going to be a poisson, but I never see anything else. And that's actually a problem. That's a huge problem because psychology frequently studies variables that are not normally distributed. That's a problem. And so I chose to talk about GLMs not because it's common, but because it needs to be common. Because these situations come up all the time where you need to do a generalized linear model. So I think most multivariate statistics class, they cover canonical correlation. They cover, what's that called? MANOVA, MANCOVA. I never see these in the literature, and I think they are totally useless procedures. So I'm not going to teach that. Instead, I'm going to teach GLMs because those are actually useful and those are actually needed. Okay, am I done with my soapbox moment now? Yes, I am. So, in summary, when data are not normal, you may choose to resort to GLMs, and this may be more common than people actually use them. So GLMs have three components: the systematic component, which is very regression-like, and just like when we use the generalized linear model, or the general linear model in the past, we can have both quantitative predictors or qualitative predictors in there. The computer doesn't care. A-okay. And it also has the link function, that is the function that curves the line, and then it has the random component, which we specify what distribution the residuals take. So in the next video, I am going to talk about evaluating the fit of the model. How do you determine whether the GLM that you have chosen is good? Well, you can do that visually or statistically. And I'm going to show you how to compare two models, both visually and statistically. I will mention comparing families or comparing the same family with different predictions. I'm not sure that I'll actually do that in the video, but it's easy enough that y'all can figure it out on your own. And then I will show you how to do GLMs in R. So with that, here are our learning objectives. And thank you very much. I'd like to thank our special guest. It has been an absolute pleasure to have you here. Thank you so much for coming and sharing your wisdom and your insight.
It really is such a pleasure.
And we'll see you next time.